For over 60 years, a really fundamental problem in computer science was thought to have a hard speed limit. I'm talking about finding the fastest way from point A to point B. An algorithm from way back in 1959 was pretty much considered the best we could ever do. But then, in 2025, a new paper comes along and does what a lot of people thought was impossible. It shattered that speed limit. So how on earth did they do it, and why is it such a big deal? Let's get into it.
So the problem itself sounds deceptively simple, right? Imagine you're standing at your front door, and you want to know the absolute shortest travel time, not just to your office, but to every single other address in your entire city. That, in a nutshell, is the massive challenge we're talking about today. And this isn't just about drawing lines on a map. This question is a core building block for so many systems we use every single day. So let's, get a little more formal about what exactly we're trying to solve here. Okay. In computer science lingo, this is called the single source shortest path problem, or SSP for short. The source is just your starting point. The vertices are all the possible destinations you could go to. And the graph is the whole network, all the roads or connections between them. The goal? Calculate the shortest path from that one source to all the other vertices. So, why do we care so much about this? Well, because SSP is the hidden engine behind countless things you use without even thinking about it. It's the brain in your GPS that finds the fastest way home. It's what zips data packets across the internet to this very device you're using. It's what optimizes shipping routes for companies like Amazon. It even helps us figure out how ideas spread through social networks. Making this one thing faster has these huge, real-world ripple effects.
For decades, the race to solve this problem was really dominated by two classic contenders, and they both came about in the late 1950s. They really represent two completely different ways of tackling the problem.
On one side, you've got Dijkstra's algorithm. It's what we call greedy. It always explores the next closest spot it knows about. It's super fast, but its big Achilles heel is that to find that next closest spot, it has to keep a sorted list of possibilities, and that sorting creates a massive bottleneck. Then on the other side, there's Bellman-Ford. It's more methodical. It just checks and rechecks all the connections. Now, it's generally slower, but its big advantage is that it doesn't need to sort anything. And that difference, right there, is the key to this whole story. Yeah, that weakness in Dijkstra's algorithm, the sorting part, it wasn't just a minor detail. For more than 60 years, it was believed to be a fundamental, unavoidable barrier, a wall you just couldn't get past.
This became known as the sorting barrier. The theory was that to find the shortest paths, you have to put them in order, from shortest to longest. It just makes sense, right? And since sorting itself has a known theoretical speed limit, computer scientists call it O(n) log n, which is just a fancy way of measuring how much slower an algorithm gets as you give it more data. It was pretty much accepted that SSSP just couldn't be solved any faster than that.
So the really crucial point here is that for generations of computer scientists, Dijkstra's algorithm was the final answer. It was taught in every textbook as the gold standard, the absolute peak of efficiency for this problem. That sorting barrier, it seemed totally unbreakable.
But the new algorithm found a way through the wall. And it did it by doing something really clever. It combined the strengths of those two old racers we just met. It kind of merges the methodical, careful nature of Bellman-Ford with the need-for-speed approach of Dijkstra.
Now, what's so cool about this is the core idea. See, Dijkstra gets bogged down sorting this huge crowd of potential next steps. The new algorithm asks a totally different question. What if we don't need to sort the whole crowd? What if we could just find a few key leaders or pivots and focus only on them?
Okay, so here's how it works. First, it looks at the frontier, that big crowd of all the places it could go next. Then, instead of sorting them, it runs a few super quick checks, kind of like how Bellman-Ford does it, just to scout ahead. And these quick checks reveal a very small but very important set of pivots. Think of them as major highway interchanges. The algorithm then just ignores the rest of the crowd and focuses all its energy on just those few pivots. It completely sidesteps the sorting bottleneck. It's genius.
And the result of this incredibly clever strategy? A genuine, measurable leap forward in performance. So, let's take a look at the new speed limit this thing sets.
So, this is the new speed limit. Now, I know this formula might look a little intimidating, but the only thing you need to look at is the exponent on that log n part. Think of it like a car's fuel efficiency. In Dijkstra's, the exponent was 1. In this new algorithm, it's 2/3. And that smaller number means that as the network gets bigger and bigger, the runtime grows much, much more slowly. It's a fundamental boost in efficiency.
And here's what that actually means in the real world. On what we call sparse graphs, which are networks like road systems or the internet, where not every single point is connected to every other point, the improvement is significant. The new algorithm just flat out gets the job done faster.
And, of course, credit where credit is due, the paper was published by a team of researchers from Tsinghua University, Stanford, and the Max Planck Institute. And one really crucial detail here is that the algorithm is deterministic. What that means is its faster performance is guaranteed every single time. It's not based on luck or randomness, which is a massive achievement all by itself.
So, okay, a faster algorithm is great. We love faster. But the real impact of this discovery goes so much deeper than just shaving a few milliseconds off your GPS calculation.
What this really represents is a fundamental improvement to one of the very first, most important algorithms that computer science students learn about. It's kind of like discovering a better way to build an arch after centuries of thinking we had it totally perfected. It proves that even the most established, settled science can still be pushed forward.
And that, right there, is the big takeaway. For decades, the sorting barrier was treated almost like a law of physics. For this problem, this incredible result proves that even the most foundational rules can and should be challenged and broken with a new way of thinking.
It really leaves us with a fascinating question, doesn't it? It just makes you wonder, what other problems that we all consider solved or unbeatable are just sitting there, waiting for one clever idea to come along and completely change everything we thought we knew?